Most people think self-driving cars just see the road, but what's actually happening under the hood? From the complete sensor stack to the perception pipeline, to the prediction module, the hardest unsolved problem in AV, we're breaking down the full engineering stack. Let's dive into how these vehicles actually make decisions. Ready to see the full engineering breakdown?
When you see an autonomous vehicle, your eyes are immediately drawn to the hardware. The spinning cylinders on the roof, the cameras tucked into the fenders, and the steering wheel turning on its own. While a robotic steering wheel looks impressive, vehicle control is a mathematically solved equation. The industry remains stuck at the 99% plateau, because the core challenge lies in the infinite variability of the world the car must navigate. This graph shows driving scenarios plotted on a power law distribution. The tall spike on the left represents everyday driving, staying in a lane, stopping at red lights, but the flat tail stretches out infinitely to the right. These are the rare, highly specific anomalies engineers call the long tail. You might drive for decades before encountering a pedestrian in a wheelchair crossing mid-block at night, or a cyclist riding the wrong way, or a fallen tree obscuring construction signs. If an autonomous vehicle drives 10,000 miles and handles 99% of situations perfectly, that remaining 1% leaves dozens of those highly complex edge cases unhandled. At highway speeds, unhandled edge cases result in fatal crashes. To understand why a billion-dollar machine gets defeated by a single unexpected detour, we have to look past the physical car entirely and descend into the invisible software architecture running it. Engineers divide this software architecture into a sequence called the AV stack. If we look at this stack in reverse, starting at the bottom where the rubber meets the road, the problems are actually quite simple. Layer 5 is control, translating a digital command into physical actuation, applying brake pressure or adjusting the steering column, is handled by established mathematical control models. Right above that is Layer 4, planning. This is where the car calculates a specific trajectory, balancing local speed limits, passenger comfort, and the rules of the road to plot a precise path forward. Both moving the car and plotting a legal route are straightforward computational tasks, provided the vehicle perfectly understands its environment. The real friction happens when the car tries to figure out the unknown future. This diagram represents Layer 3 of the stack, prediction. This is the hardest unsolved problem in the industry. As a pedestrian steps off the curb, the software attempts to anticipate their intent. The potential trajectory lines multiply rapidly, creating an uncertainty explosion. Because human behavior is chaotic, the software struggles to assign probabilities, suffering from the freezing robot problem, halting completely. To make those predictions, the car first relies on Layer 2, perception. It has to ingest millions of raw data points per second to build a structured, real-world environment model to understand the present moment. That data comes from Layer 1, the sensor stack. Most vehicles start with high-resolution cameras to capture dense semantic details, reading things like lane lines and traffic lights. But cameras go blind in direct solar glare, heavy rain, or fog. To compensate, many developers use LiDAR. This sensor emits pulses of near-infrared light to construct a highly accurate 3D map. It provides precise distance measurements of the physical geometry, but it degrades in heavy weather and requires incredibly expensive hardware. That leaves radar, which lacks the visual detail of cameras and the spatial resolution of LiDAR, but easily penetrates fog and snow to measure the direct velocity of moving objects. A vehicle can have perfect, overlapping arrays of multimodal sensors mapping the present moment. But if the software brain cannot intuit the unpredictable behavior of human beings, the entire system fails. Every major developer works within this same software stack, but the industry is divided by two competing engineering philosophies for solving that endless tail of edge cases. Companies like Waymo build highly modular systems. They rely on heavy sensor redundancy and map their operating areas with centimeter-level 3D accuracy, providing the vehicle with a perfect prior understanding of the road. This heavy integration produces a verifiable safety record, but the hardware is incredibly expensive, and the vehicles are strictly geofenced, meaning they can only operate in pre-mapped urban environments. Tesla takes an opposing, map-free approach. They rely entirely on an end-to-end neural network fed purely by camera vision. Their operating logic is that if human beings can navigate the world with two eyes and a brain, A machine should be able to do the same with cameras and a neural net. The vulnerability of the end-to-end approach is opacity. If the neural network misinterprets a rare edge case, it acts as a black box. Engineers cannot simply look at the code and untangle exactly why the system made the wrong decision. Closing that final 1% gap involves a multi-decade scientific effort to teach machines human intuition. The hardest part of building a self-driving car is predicting the people sharing the road.
From the sensor stack to the planning system, we've broken down exactly how these vehicles perceive and navigate the world. Whether it's solving the perception pipeline or tackling the prediction module, the engineering reality of reaching full autonomy is a massive challenge, and the debate between HD maps and map-free architectures continues to define how we bridge that final gap to global deployment. If you enjoyed this technical breakdown, hit that like button and subscribe for more deep dives. I'll see you in the next one.